Welcome back to Mathematics 2. Today we're going to see how to apply the theory we developed so far to actually diagonalize a matrix. We're going to learn how to characterize matrices that can be diagonalized over the complex numbers, and we're going to see how to apply this in practice. So this is a new section, 11.5, matrix diagonalization. Let's start by stating our goal once more. So the idea here is what we want to do is we want to characterize which matrices can be transformed into diagonal form. So characterize which matrices can be transformed into diagonal form, meaning they possess a basis that consists of eigenvectors. So they possess an eigenvector basis. Before we dig deeper into that, let's first define precisely what it means. So a matrix is called diagonalizable if there exists a basis of Rn that consists of eigenvectors of A. That's a definition. A matrix A in R to the n times n is called diagonalizable if there is a basis of R to the n that consists of eigenvectors of A. And let's generalize this notion just a little bit. We do not necessarily require a basis of R to the n, but we would be happy with a basis of C to the n as well. So if we need to use complex numbers and complex eigenvectors, then we will happily do that. Okay, so far we already know one thing. We know that if we have an eigenvalue, then of course there must also be a corresponding eigenvector to that. Okay, so for each eigenvalue there is at least one eigenvector. Question is, what can we say about the number of eigenvectors that can be associated to an eigenvalue? Well, we're just talking about the number, then of course that is infinite, because every multiple of an eigenvector is again an eigenvector, and you can have infinitely many of those. So the interesting quantity here is the dimension of the eigenspace. How many linearly independent eigenvectors can we find? So the question is there a bound to that? And how can we tell if there might possibly be enough? How many should there be for each eigenvalue? Let's take note of these thoughts first before we define the necessary quantities, and then hopefully answer that question. So we know already that for each eigenvalue there is at least one eigenvector okay, meaning the dimension of the eigenspace of lambda is at least 1 for each eigenvalue lambda. So what that means already is if we have n distinct eigenvalues, then we can be sure that there is a basis of eigenvectors. So if A possesses n distinct eigenvalues, then there are at least n eigenvectors. Of course, what does remain is the question of whether these form a basis. So do they necessarily have to be linearly independent? And that's a question that we're going to solve in just a minute. Before that, let's establish an upper bound as well. So if we have an eigenvalue, how many linearly independent eigenvectors can there be for that specific eigenvalue? And one can show that this is related to the multiplicity of the root of that eigenvalue in the characteristic polynomial. So that's what we are going to formalize in a minute. One can show that the multiplicity of a root lambda in PA, the characteristic polynomial, is an upper bound to the dimension of the eigenspace associated to that lambda. So to make this a little more explicit and more precise, we'll define names for these multiplicities that we want. Specifically, we call the multiplicity of the root lambda in the characteristic polynomial. We call that the algebraic multiplicity of an eigenvalue. And the dimension of the eigenspace associated with the eigenvalue is going to be called the geometric multiplicity of the eigenvalue. Okay, so let's define that first. Use that definition. Let A in our n to the n and let's consider lambda star in C, and let that be an eigenvalue of A. Furthermore, let K be the multiplicity of that eigenvalue. So further, let K be the multiplicity of the root lambda star in PA of lambda. That means, well, what does that mean? That means there exists a polynomial G of lambda with the following properties. Well, PA of lambda can be written in the form lambda minus lambda star. So that's this linear factor corresponding to the root lambda star. And that has multiplicity k. So we have that factor to the k times whatever remains, and this is this g part here, whatever remains of the characteristic polynomial. And this g part does not have the root lambda star anymore, so the k is maximum. Okay, so g of lambda star is not 0. Then k is called the algebraic multiplicity of lambda star, and the dimension of the eigenspace associated with lambda star, this here, is called geometric multiplicity. Of lambda star. Okay, and with these terms in mind, we can now formulate the following theorem. For a matrix A in R to the n times n, the following hold. 1. For each eigenvalue, the geometric multiplicity is at most equal to the algebraic multiplicity. So the algebraic multiplicity is an upper bound on the number of linearly independent eigenvectors for that eigenvalue. Okay, for each eigenvalue lambda in C of A, the geometric multiplicity is less or equal to the algebraic multiplicity. So what that means is we can find at most algebraic multiplicity many eigenvectors that are independent. So in order to get a basis, we have to find exactly that number. And we have to guarantee that the eigenvectors for distinct eigenvalues are actually linearly independent. And that is part 2 of that theorem that guarantees us just that. For pairwise distinct eigenvalues, lambda 1 to lambda r of A with corresponding eigenvectors so we take any eigenvectors here, V1 to VR, one for each eigenvalue, the set V1 to VR is linearly independent. Okay, and of course we can easily extend that to more than just one eigenvector per eigenvalue. If we have more than one independent eigenvector, we can also use that. And finally, the conclusion. The matrix A is diagonalizable over C. So we may need to use complex eigenvalues and complex eigenvectors if and only if algebraic and geometric multiplicity are equal for every eigenvalue of A. Okay, so that's the criterion we've been looking for. We can determine the algebraic multiplicity by just finding all the roots and their multiplicities in the characteristic polynomial. And after we've done that, we can determine a basis for the eigenspaces. We are guaranteed that the bases that we find for different eigenvalues are linearly independent. So if we just put all of these bases together, we get a basis of the R to the n if and only if the geometric multiplicities are as high as the algebraic multiplicities. So that's the whole point here. Okay, I'm not going to prove all of that theorem, but I'd like to point out just a small part of that. So we are going to prove a simplified version of part 2 of that independence, so that you see how this is actually working. It's not hard to see. So we're proving this part 2 here. And specifically, we're proving it for R equals 2. So 2 distinct eigenvalues. Okay, so let lambda 1, lambda 2 be eigenvalues. And let's say we have corresponding eigenvectors v1, v2. So those are eigenvectors. And we want to prove that these eigenvectors are linearly independent. So let mu1, mu2 be coefficients such that mu1 v1 plus mu2 v2 equals 0. And we need to show that the mu's necessarily have to be 0 then. Okay, well, what can we see from that? So we just can multiply all of this by lambda 1 or lambda 2. Let's use lambda 2 first. The whole equation multiplied by lambda 2 looks like this here. And of course, lambda 2 times 0 is again 0. And we can also apply A to that whole equation. So if we do that, then A times mu1 v1 plus mu2 v2 is of course also 0. Okay, that means, well, from the first equation, what we get is simply mu1 lambda 2 v1 plus mu2 lambda 2 v2 is 0. And from the second equation, what we get is mu1 a times v1, a times v1 is lambda 1 v1 plus mu2 a times v2, and that times v2 is lambda 2 v2. Right, so these here, this is equal to a v1 and this is equal to a v2 because v1 and v2 are eigenvectors. Okay, now if we just take the difference of these two, let's give those names. So let's say this is equation 1, this is equation 2, and now we're taking the difference here. Let's say 1 minus 2. Then what do we get? Well, we get that first factor, mu1 v1 lambda 2 minus lambda 1. And the second factor is the same, so that just vanishes, and the right hand side is 0 in both cases. Okay, so what can we see from that? Well, the eigenvectors here, those were distinct, so this is not 0, this factor here. Also, the vector v1 is an eigenvector, so it cannot be the 0 vector. And that means the only way that this expression can be 0 is mu1 needs to be 0. Okay, so we found mu1 already. Well, if mu1 is necessarily 0, then this means our expression mu1 v1 plus mu2 v2 equals 0. This reduces to mu2 v2 equals 0. And again, v2 is an eigenvector, so v2 cannot be the 0 vector. And that means mu2 has to be 0, because v2 is not. And again, that's because we have an eigenvector. So finally what we have is mu1 is 0 and mu2 is 0. So we've shown that the set v1, v2 is actually linearly independent. Okay, that concludes the proof. And of course this can be extended to any finite number of eigenvectors and eigenvalues. Okay, so now we know how to find out if a matrix can be diagonalized, and we also know how to actually diagonalize it. We're going to see a brief example in the next video, and then we are finally going to apply this theory to the solution of systems of differential equations.